We are Íñigo Andreu, Tony Balaguer, and Joan Font, and we'll solve exercise 5.7. The main aim of this exercise is to compute the magnitude and direction of a magnetic field which is experienced throughout the length of a wire ring suspended in space. This particular wire ring carries a certain current which flows in a clockwise direction and is affected by a magnetic field B. This magnetic field crosses the wire ring with a certain theta angle. The magnetic field then sources or expands radially from a point far below the ring. The first step then is to set a theoretical background on which we'll proceed during the resolution of this problem. As we're talking about magnetic forces, we have to remember the Lorentz force, which is stated that the magnetic force exerted on any particle in space is proportional to its charge and perpendicular to the plane formed by the velocity vector and the magnetic field that is affecting the particle. Recall that the operator found in this expression, the cross product, returns the perpendicular vector to the ones operated. By looking at this diagram, we can notice that the magnetic force is perpendicular to the velocity v and to the magnetic field B, which they form a plane. This kind of setting follows the right-hand rule, where fingers form the plane and our thumb will specify the direction of the magnetic force. As we're talking about a wire, we can do the next transformation. We can apply the equivalence between charge and velocity with the current which carries the wire and the length of the wire itself. Now, as we have to find the force for each point that is found throughout the length of the wire, we'll use the following expression, in which the magnetic force is integrated along the path for each small portion of length of the ring. This is because we're found in a continuous charge distribution exercise.
Once we have understood the problem, we will plan the route. We will consider first a small portion dl of the ring. Then we will test how the entire ring reacts, and eventually we will calculate the force. So first, let's just take into account a small portion dl. At this point, the magnetic field is inclined at an angle theta to the normal of the plane. The force here must be perpendicular to the magnetic field and dl due to the cross product. This portion has the differential of force dF with two components, the horizontal and vertical. It's easy to see by basic trigonometrics that the magnetic field angle is the same of the force, as we can see in the draw. Now, we must recall one basic concept, symmetry. All the portions in the ring have the exact same force components. Due to the cylindrical symmetry of the ring, the horizontal component, which points towards the center of the ring, will vanish. So the total net force is produced by the vertical component, which points upwards. However, we must recall that inside the force formula we have another angle. Let's call it alpha. This alpha can be neglected since it is the angle between the magnetic field and dl, and has a value of 90 degrees. Now we know how the ring will behave in this context. We only have to substitute and to take outside the constant values. Finally, we compute a trivial integral that goes from 0 to 2 pi a, and we obtain our solution, which obviously is in the z-axis.
We just calculated the magnitude of the force, so now we have to indicate its direction. All the portions in the ring have the same force components, cos the angle is the same everywhere. As we said, since we have cylindrical symmetry and the x component of the force points towards the center, all x components will vanish, so the total net force is produced only by the y components. Once the exercise is solved, we should ask ourselves for possible similar situations or possible variations of this exercise that could help us solve new ones in the future. It's quite interesting if we wonder what would happen if the current flowed the other way around. In this case, the procedure to solve the exercise would be the same. However, as it is shown in the picture below, each force generated on each portion of the ring would point in diagonal downwards, So again, all the forces in the x-axis would cancel each other, and the net force would point downwards. Another interesting thing to consider is trying to find the best angle to maximize the resulting force. First, let's remember that the angle we are talking about is the one given in the exercise, the one that forms the vector of the magnetic field and the normal of the ring. As we said before, there exists symmetrical symmetry in this exercise, so we want that forces don't cancel each other. As it is shown in the picture, the best angle is of 90 degrees, because the cross product gives us a force pointing upwards in each part of the ring, so they are all parallel. Last but not least, if the angle we just talked about was of 0 degrees, all forces would be in the same plane as the ring, pointing to the center, so they would cancel each other and the net force would be of 0 newtons.